Welcome, future engineers. Let's dive right into this explainer. We've all been there, right? Staring down a page literally covered in tangled, messy equations, just wondering how on earth to organize them all. Well, today, we're taking abstract math and transforming it into your absolute most powerful problem-solving toolkit. We're going to bring some serious order to that chaos.
So, here's our lesson plan for today. We'll start with the bungee jumper problem, move on to matrix types and notation, tackle basic matrix operations, look at calculating the determinant, and wrap up with identity and inverse matrices.
Section 1. The bungee jumper problem. The messy reality of linear equations. Let's kick things off with a classic real-world engineering villain. Picture this: 3 interconnected bungee jumpers dangling in midair. They're being pulled down by gravity, sure, but they're simultaneously held back by the spring constants of the cords connecting them to each other. So, how do we calculate the exact displacement of these 3 jumpers once they hit equilibrium? It's a simple question, but it creates an immediate, very tangible need for the math tools we're about to build.
If we apply Newton's second law and Hooke's law for linear springs and set the steady-state acceleration to 0, we are left with 3 simultaneous linear equations. And they are a mess. Thinking about these interconnected equations, it is crystal clear we need an ultimate organizing system. I mean, having variables like K1, K2, and M3 just scattered everywhere, that is exactly why we desperately need a better way to structure our data.
Section 2. Matrix types and notation. Building the data container. Let's talk about how we turn those messy equations into what is essentially a highly structured spreadsheet. I want you to think of this n by n matrix not as some abstract math concept, but as a rigid data container. Every single row and column has a physical meaning. The rows are horizontal sets of elements, like say all the forces acting on jumper 1, while the columns are vertical. We use the notation Aij to pinpoint an exact element. The I tells you the row and the J tells you the column. Pretty straightforward, right?
As we expand our toolkit, we start running into special shapes. Take the symmetric matrix, for example. This one pops up in physical system models all the time. It's a square matrix, meaning it has the exact same number of rows and columns, and the elements mirror each other perfectly right across the main diagonal. Basically, if you were to transpose it, flip the rows into columns, the matrix remains exactly the same, no change whatsoever. And that idea builds directly into the diagonal matrix, which, let me tell you, is a real game changer. It drastically simplifies our engineering calculations by clearing out all the clutter. In a diagonal matrix, every single element that isn't on that main slice, from the top left down to the bottom right, is just a 0. It focuses all our attention solely on the diagonal elements, which makes all our later operations incredibly clean.
Which brings us to a brilliant concept, the identity matrix. This acts exactly like the number 1 in our matrix universe. It's just a specific type of diagonal matrix where every element on that main diagonal is exactly the number 1. If you multiply any matrix by an identity matrix of the right size, you get your original matrix back completely unchanged. It is literally a foundational pillar of matrix algebra.
Section 3. Basic matrix operations. The rules of engagement.
Okay, so we've built our data containers. But before we can actually rescue those bungee jumpers, we need to know how to add and scale these things. These are your rules of engagement. And honestly, they prove that basic matrix operations behave very similarly to the regular algebra you already know and love. The absolute biggest rule: addition and subtraction can only happen between matrices that share the exact same dimensions. You simply cannot add a 2x3 matrix to a 3x3 matrix. It just won't work. But just like regular numbers, matrix addition is commutative and associative. Oh, and multiplying by an outside number, a scalar, distributes perfectly across all the elements.
So the crucial takeaway here is that whether you're scaling forces or adding displacements, you apply the operation to the corresponding individual elements. For scalar multiplication, that outside value scales every single entry inside the matrix. For matrix addition, you just add the term in row 1, column 1 of the first matrix to the term in row 1, column 1 of the second matrix, and so on. It is highly systematic and perfectly orderly.
Section 4. Calculating the determinant. The heavy lifter of matrix algebra.
But wait, before we find the determinant to do that heavy lifting, we've got to talk about matrix multiplication, because this is where the rules of our parallel matrix universe really start to bend. Comparing scalar algebra to matrix multiplication highlights a huge, mind-bending pitfall for new learners. In matrix multiplication, order absolutely matters. In normal scalar algebra, sure, 3 times 4 equals 4 times 3. But in matrix algebra, matrix A times matrix B generally does not equal matrix B times matrix A. No way.
And it gets trickier. You can't just multiply any two matrices together. Their inner dimensions must perfectly interlock, kind of like puzzle pieces. So if you have an m by n matrix, you can only multiply it by a matrix that has n rows. The exterior dimensions, m and l, will then define the exact size of a resulting matrix. As for the actual math, you multiply the elements of a row in the first matrix by the corresponding elements of a column in the second matrix, and then sum them up.
So, why do we care about calculating the determinant using this simple algorithm? Well, because without it, finding our final solution is quite literally impossible. Now, for a simple 2 by 2 matrix, finding the determinant is a breeze. You multiply the main diagonal, you multiply the off diagonal, and you subtract the second product from the first. Simple. For a 3 by 3 matrix, sure, it involves cofactors and a bit more arithmetic, but the core reason we do it remains exactly the same.
The determinant is an absolutely critical value. It determines if a square matrix is non-singular and if it actually has an inverse. We engineers might joke about the pain of calculating massive 3 by 3 determinants by hand, breaking them down into those smaller 2 by 2 cofactor matrices, but this single number is the gatekeeper to solving our entire system. If a determinant is 0, the matrix has no inverse, and if there's no inverse, we can't solve for our bungee jumper's displacement. It's a dead end.
Section 5. Identity and inverse matrices, the keys to the solution. All right, we have officially reached the final tools in our engineering toolkit. These are the exact instruments we need to finally rescue our bungee jumpers from mathematical limbo. Treat this formula with the gravity of a universal law in engineering, okay? Multiplying a matrix by its inverse yields the identity matrix. Remember how we said the identity matrix acts like the number 1? Well, this formula is the exact matrix equivalent of saying 5 times 1/5 equals 1. If we can just find the inverse of our coefficient matrix, we can effectively divide away all those complex spring constants and isolate our unknowns.
By following these 3 simple steps, we leverage that inverse matrix to completely unravel the tangled mathematical web of our 3 jumpers. First, we take those messy original equations and write them as a clean matrix equation. Matrix A, containing our constants, times column vector x, our unknown displacements, equals column vector b, our gravity forces. Then, we simply multiply both sides by the inverse of A. Because A inverse times A becomes the identity matrix, our unknown vector x is completely, cleanly isolated. Multiplying by an inverse is basically the matrix equivalent of division. It elegantly isolates the exact physical displacements we need. And honestly, this brilliantly illustrates how matrix algebra isn't just a bunch of abstract rules to memorize. It's a highly efficient machine for dividing out complexity, so we can find the exact engineering answer. We took a chaotic interconnected physical system, neatly packed it into data containers, followed the rigid rules of multiplication, found our determinant to unlock the inverse, and arrived at a clean, precise solution. The whole shebang. So, keep this powerful toolkit ready, because as future engineers, solving interconnected systems is exactly what you were born to do. Matrices are literally the language of modern engineering. Whether you're mapping out massive electrical grids, optimizing the kinematics of robotic arms, or ensuring the structural integrity of a skyscraper. So now that you have the ultimate matrix toolkit, what complex physical system will you solve next? Stay curious, and I'll catch you on the next explainer.